So it's really a pleasure and an honor to be here to talk about what has been a great collaboration between NASA and Keck going back over 30 years, and I'll talk a little bit about that. I've been part of it for a good fraction of that. Certainly more than 20 in my role as a selection official for the NASA Keck time. So I'll give an idea, a little bit of the history, talk about some of the fruits of the collaboration between NASA and Keck on some individual science areas, technology, and maybe end up with a few future thoughts. So let me go ahead, and which button to press? So first, NASA goals and ground-based astronomy. I mean, NASA has many strategic plans. They change sometimes, not very often, sometimes frequently. So the best current statement of that actually comes from Nikki Fox, who's the current Associate Administrator for Science Mission Directorate, that astrophysics is humankind's scientific quest to discover the origin of the universe and of life itself. 3 questions: how does the universe work? How do we get there? Are we alone? Form the basis of the 3 astrophysics science themes. And that's pretty recent. That's as recent as March. And so it really reflects the commitment the NASA Science Directorate has to doing astrophysics. So what is the role of ground-based astronomy in that? That's encapsulated in this quote here, that NASA doesn't do ground-based astronomy until it does. And that goes back to, Ed Weiler, has been restated many times by other astrophysics directors and SMD directors over time. And we're here today, or I'm here today, because of the exception. We are the until it does, and there's a lot of reasons why Keck has been critical to the development of NASA science. So in the beginning, back in 1992, there was something called the TOPS report towards other planetary systems, and it laid out a program that has turned out to be very prescient. So TOPS was centered on a ground-based observing program to find other planets. So this is well before 51 PEG. We want to discover and study planets with masses as low as Uranus and Neptune, around 100 or more stars in the solar neighborhood. The defining element of TOPS 0, this first phase, is the Keck 2 telescope. And that would involve the construction of Keck 2, enhancing the image quality of the telescope through adaptive optics, focal plane instrumentation for studying planetary phenomena and material around other stars. That would include both studying solar system objects and looking for debris disks, which are known about from IRAS and Spitzer, and building an interferometer using the 2 Keck telescopes. That was built in from the beginning. And all of those came to pass. And so that's what I call the beginning of a beautiful friendship. And if you don't know this quote, just go home, because you're not going to like the rest of my talk. So I want to go through then, discussing some of the science results that came in sort of these 3 different areas. So solar system science, extragalactic science, and then some exoplanet science. I'll talk a little bit about instruments and technology, where Keck has played a key role in helping NASA with some of its goals. I'll talk a little bit about how the community accesses both time on the Keck telescopes, but then also get to the data, and then talk a little bit about the future. So let's talk a bit about solar system science. I mean, this goes back really to the beginning. Once NASA Keck time became available, the science was actually restricted to either solar system science or exoplanet science. That started to grow with time, but originally those were the 2 themes he could propose for time on Keck through NASA. And it's really been, just many, many years of dramatic results. This is one of the recent ones where they had a recent press release of comparing a JWST near-cam image, um, you know, looking at the weather on Titan, and you can see clouds coming and going. And then a few days later, using NERC2 in the AO system, remember that image sharpening goal came to pass, and you can actually see, again, just a spectacular, image taken with NERC2 following the evolution of the clouds on Titan. And, why is this of interest to NASA? Well, of course, NASA has had past, spacecraft looking at Saturn and Titan, and also in the future, there'll actually be a drone quadcopter going to fly around on Titan as well, with Dragonfly launching in a couple of years and actually getting to Titan sometime around 2032. So hopefully Keck will be able to be supporting that in the many years to come. If we go closer in the solar system, here we have asteroid 2024 YR. Who are you going to call? Well, this thing had a Torino rating, which relates the what would happen if this thing hit the Earth of 3. That's roughly like a Tunguska class impact. And the impact probability on Earth was about 3% for an impact around December 22, 2032. This actually generated for the first time the activation of the planetary defense protocols. That is a very formalized structure that goes up through NASA's Office of Planetary Defense, through the US government, the security services in the US, the military, and all the way up into the United Nations. Additional astrometry, including, from Keck, shown here, from Melissa Brucker and other people putting together LRIS images, show that the Earth was safe, but as we heard from Bryce yesterday, there's still about a 4% chance that 2024 YR will hit the moon, which would be spectacular, we hope, but not dangerous. And I'll point out, and this is something where I think Keck will have a role to play, that the NEO Surveyor satellite, which is sort of a version of WISE and NEO-WISE, but focused clearly on doing near-Earth asteroid observations, sitting at L1, looking interior to the inner parts of the solar system, launches in about 2029, and it'll detect many, many potentially hazardous asteroids down to a diameter of 1/10 of a kilometer or so. And I think there will be a role for Keck, not so much to do the fast response, but to characterize these objects spectroscopically and just understand more about them. And that would mean that Keck would have to start operating in both morning and evening twilight, since that's where those objects tend to be found. But I think it's an interesting role for Keck to play as NEO Surveyor goes up. And just in the current budget climate, I will point out that planetary defense and NEO Surveyor were the only part of NASA Science Directorate to get a budget increase. It is part of the Golden Dome, kids. What can I say? We already heard from Bryce a little bit about the interstellar comet 3I Atlas. We heard about that. We had Keck playing a role in that through some DDT time. And we were able to get both imaging and the spectrum that Bryce showed yesterday. There's also a JWST spectrum that is pretty flat in the area where Keck was able to observe it, but much richer as you go out to the longer wavelengths accessible to JWST NIRSpec. As we start ramping up with things like Rubin, and then in other facilities where these interstellar tourists are going to be more prominent and more frequent, again, I think there'll be a role for Keck and the space missions to start characterizing these objects and hopefully show that these are not alien spacecraft. If we shift to extragalactic science, the last 2 days have been filled with talks that really highlight the role of Keck, by itself doing fabulous extragalactic science, but also Keck in conjunction with the various NASA assets. And that, of course, will be coming in the future. And Keck has played really a key role in supporting some of these missions. I'd highlight the program that was put together as a Keck Key Mission Support Program, but it was also allocated many nights from Keck Partners, which was to take the photometric redshifts that Euclid and Roman would be using to characterize most of its galaxies, but actually get spectroscopic calibration for those objects and use that to have a very finely tuned way to use the photometric redshifts to do all the weak lensing cosmology that Roman and Euclid will be doing. So the team that did this, combination of JPL, Caltech, and other people, developed a scheme where they would take all the different colors that Euclid and Roman would be using, populate this map and say, okay, which objects need to be observed, using a way to organize all the different colors, and then start to fill in all the blank areas to say, if I get this combination of colors photometrically, what is the actual redshift that corresponds to that? And they got, with over 50 nights of telescope time from NASA and other partners, 8,000 spectra, 5,000 redshifts for galaxies as faint as 25th AB. And it covers about 90% of the Euclid color space. All the data are available, and you can see that we get a very nice relationship between the photometric and the spectroscopic redshifts with very low scatter and very low bias, and that's a lot of almost all of what Euclid needs. Roman goes deeper, and so it's a bit more of a challenge, and I think some of that may still be ongoing. But that was a clear relationship between a need for a space mission, and NASA had a key role in Euclid, and then, of course, in Roman, where Keck played a key role. Just, I'm sort of more serendipitously, Keck and JW identified a super massive black hole in a cosmos field of a pair of galaxies, where the black hole is not in the core of one galaxy or another, but actually at the interface of the pair of colliding galaxies. And the Keck data and the spectroscopy were key in working out what was going on in that system. Obviously, transit phenomenon, multi-messenger is a big thing. The CHIME radio telescopes identify fast radio bursts. CHIME now has a capability with interferometry to localize the objects at very high precision at the millisecond level. That allows then both Keck and JWST to go in and characterize in detail the host object and the environment where the FRB is located. On the cosmology side, of course, Keck and Hubble worked together with their supernova surveys to yield, one Nobel Prize for really the discovery of dark energy through the supernova work. And from what we've been hearing, resolving the Hubble tension will also probably involve a combination of space facilities and facilities like Keck to resolve the Hubble tension and possibly get us to a second Nobel Prize in this area. So lots and lots of science in the extragalactic world, and that's clearly a key part of what Keck does, and on its own and in support of various NASA missions, particularly now JW. Let me shift a little bit closer to the research I've been more involved in recent years is exoplanet missions, and obviously there's a huge range of NASA missions that have been working on this, from Kepler and TESS, Webb, Roman coming up, Pandora launching in a couple of months, Ariel going up in a couple of years. So if we look at the growth of exoplanets since 1995, starts out pretty slowly, a lot of RV observations, many of them coming from Keck in the early years. There's over 150 pure Keck discoveries from RV, and especially in the early years. or really it was Keck and the Swiss group doing all this, but you know, it continues to grow. The transits come in, start giving us a whole new view. And of course, transits have now become the dominant contributor of exoplanets. And we're now up to, just the last week, we announced over 6,000 confirmed exoplanets. And so where does, you know, Keck fit into this? The sort of things that we're looking at with where Keck plays a key role is in confirmation of a lot of the RV systems and the transit systems, Keck and KPF and HiRes doing discoveries in RV space, young planet imaging up in the more distant, more massive objects, and microlensing helping to characterize some of the microlensing objects. And as I mentioned, Keck discoveries since 1998 are like 180 purely Keck discoveries. If you go into the ExoFOP, which gathers data on all the different confirmed or candidate planets from NERC2, there's something like 1,400 individual observations, 940 unique objects. Dave Ciardi has probably observed the vast majority of those. With HiRes, almost 6,000 observations of more than 2,000 unique targets, many of those, of course, Kepler, K2, and TESS objects. So Keck has played a key role, but how does that map into what we now want to learn from these 6,000 confirmed planets? At some point you say, okay, enough already. Why do we care about 6,001 planets? Well, it actually has to do with understanding the demographics of planets by putting all of these different techniques together to build up a complete picture. So there's a whole role for Keck, and let's see if I can make this go. Maybe that'll start to go. Yes. So we have imaging, we have radial velocities, we have transits, we have disks, we have astrometry, and we put all those together, we get an idea of what the demographics of exoplanets really are. And that we can begin to relate to formation mechanisms and evolution of planetary systems. So how does Keck play a role in each of these areas? Well, of course, there's imaging, and we have the fabulous movie that Jason put together about HR 8799 and its planets rotating around their host star. This is a planetary system. What can you say? But we also do other things with imaging. There's now with KPIC imaging spectroscopy, where you can get these, R of 20 and 30,000 spectra of planets. So we're really learning a lot from the imaging, and the goal of facilities like, KPIC and then high-spec coming in the future is to be able to do more of this with imaging. Scales will come along as well. Radial velocity, of course, just major contributions out of Keck from first HiRes and KPF, and really mapping out what is the distribution of giant planets, peaking at a few AU, not so many in the interior, hot Jupiters being the exception, and then it looks like there's a fall off as you get outside of the snow line. So this has been a major contribution coming out of Keck. Transits, of course, has been just blown wide open, with Kepler, K2, and TESS, and in each case, there have been major contributions by Keck. Early on, we were devoting 20 or 30 nights per semester of NASA Keck time directly to follow-up and confirmation of Kepler targets, and that's been really a steady drumbeat of what Kepler and K2 and TESS have relied on Keck for. Imaging to show that you actually don't have a binary system, or if you do, you can understand its effects. Rossler McLaughlin to get an idea of inclination of the planet relative to the spin of the star. The whole Fulton Gap, where you understand that there's smaller planets, lower mass, high density planets in close, and then the more massive planets having a totally separate distribution. And that all came out of the combination of transits with RV work coming out of Keck. But beyond that, We have microlensing, and there's a certain amount that Keck imaging can do to try to break some of the degeneracies as the lens star and the source star start to separate. You can image both of them with high resolution imaging and learn a lot more about the system as you break some of the degeneracies in the modeling. People are now starting to use the dynamics in disks that you see with ALMA. You see a kink in the disk. Is there a planet there? Is it something else? People are starting to say, well, maybe there actually is a planet at the source of one of the dislocations in the disk. So postdoc of Dimitri and mine, Taichi Uyama and Dimitri have been exploring this in a Herbig AE-BE star disk, and maybe there's a planet located in that system somewhere. Finally, there's astrometry. There's a very long and sad tale about all of that. Remember that interferometer I talked about early on? We could have been a contender. If you look at what the gravity system is doing on the VLT, we were 20 years ahead of them, and it just didn't work out. We couldn't build 4 2-meter telescopes in the parking lot. And for a variety of reasons, NASA moved on from that. And but this was an early goal of the interferometer, was to do the astrometry to be able to find planets astrometrically. But nonetheless, even with the single telescope, we're able to do fabulous work with astrometry. Quinn Konopacki was able to do astrometry of the HR 8799 system. Starting to now use Gaia with accelerating stars. Brendan and Kyle were able to pull out a planet based on the predicted acceleration and predicting where the planet might be, and starting to find that. So astrometry will start to take off with the release of Gaia, and we'll get a lot of imaging systems that we'll be starting to observe with Keck and other facilities. So let me come and talk a little bit about instrumentation and technology and how NASA and Keck have worked together in those areas. And I think it's been a very rich and productive collaboration. Supporting JWST, going back to the very earliest days of JW, there was work to demonstrate the fundamental concept of doing the alignment of the different telescope segments by using what was called a dispersed Hartmann sensor to actually capture the edges of all the different segments and pull them together. And this was test done by moving the segments around on Keck, using the DHS technique, and reducing the offsets from 25 microns down to 0.2 microns before and after. And that was really a key part of validating the technology of JWST. Much later on, we were able to use MOSFIRE to help get the data that would eventually be used to calibrate the NIRSPEC IFU. And just before launch, there were some very nervous managers of JWST saying, look, what if the segments are completely thrown out of whack? How are we going to recover them? That was called the lost in space scenario. And we actually used MOSFIRE and pushed all the different segments into completely random positions, and were able to show that it was possible to recover them and do the stacking. And wasn't necessary. The segments stayed very well positioned after launch, so that wasn't necessary, but just making NASA feel comfortable was seen as a major contribution to lowering the blood pressure at NASA headquarters and at Goddard. We're now starting to do similar levels of support for HWO. We've started to allocate about 7 nights per semester for the next 3 years to help refine the mission concept and also the architecture. There's precursor science to help understand whether the targets that HWO has, and Eric Mamajek put together a list of 150 or so targets, but do they have a giant planet or even a Neptune sweeping through the habitable zone? That could eliminate that particular target from being a viable candidate for HWO to find a habitable zone Earth. Are there companions that we could find with imaging? So there's 2 science programs that have been selected to do that. There's technology development. Of course, the vector vortex was pioneered. at Keck and is, one of the key ideas for HWO coronagraphic masking. Rebecca Jensen-Clem has a program to use the Zernike wavefront sensor to try and explore possible wavefront control algorithms to be used on HWO, but test them out with another large segmented telescope. I mean, there are differences, obviously, of time scale and scope and precision, but it's still something that NASA is very interested in pursuing. Again, NASA does not support Keck instruments until it does. So the original high-res was a 1 CCD instrument, and that was upgraded in 2004 to 3 detectors, greatly boosting, the UV performance, but also improving, and NASA didn't care about that. John Merrick maybe cared about it, but not NASA, but it improved the PRV capability enormously, and that was the main reason NASA did that, and it was obviously working well to this day. For scales, we brought one JWST H2RG to use for scales, and for high spec, we're using one H2RG for the guider and 2 Roman H4RGs for the main instrument. And John and I each had the privilege of carrying $1 million worth of hand luggage across the country, bringing it from Goddard to Caltech. And if you don't think we were nervous, we were. One non-NASA project that I just want to highlight, because it's something I've been working on for a decade, is to bring a laser frequency comb up to the near-infrared instruments for use in both precision radio velocity of cool stars, but also giving us a fabulous line frequency, a line shape reference across the entire spectrum to be used for transit work or anything else. So Stephanie Leifer and I have been pursuing this for a long time. We started out in 2015 testing LFCs at Keck, using NIRSpec, working with Greg Dotman and other people. And finally, we're able to get a Heising-Simons grant to actually get something built and getting it on into the basement at Keck, where it's now working with NIRSpec and KPIC. And you can see some of the data here with Barnard Star and the LFC lines in here, and working with Caitlin Horseman and other people in Dimitri's group, we're able to stabilize NIRSpec to better than 10 meters per second. So it's not down at where we finally will expect to be once we get to high spec, but we're at the point where now we'll be able to do good stable RV work at infrared wavelengths. So let's come back and talk a little bit about how you access data, from Keck. How do you do mission support? This is just sort of a word cloud of some of the missions we've been supporting over the last, 10 or 12 years. So how do you access NASA Keck time? I'll just go through this very briefly. We get about 90 nights a semester. The oversubscription rate is something like 5 or 7 to 1. All the modes and instruments are available, reviewed with dual anonymous review. Don Gelino helped pioneer that for the first dual anonymous review for the ground-based telescopes. You can put in general observer proposals. That's roughly a half to 2/3 of the nights. We grade them on their science and feasibility, but also their strategic alignment with NASA goals. There's strategic mission support proposals that have to be very aligned, typically with a NASA mission or a very specific goal. And then headquarters or another partner can also allocate time on Keck, either through, say, the JWST TAC or the aerial mission, or, as I mentioned earlier, the HWO proprietary science program. So the NASA Access has broadened the accessibility of Keck to the US community. So this is just a map showing where all of our NASA observers have come from over the years. Certainly a lot of people from California, grad students from UC, or people who, quote, have partner access into Keck, but maybe they don't because they're a grad student or a postdoc or something, can still get access. But there's many people across the country who now get access to Keck. And I think that just helps Keck being perceived as a national facility as one puts in proposals for instrumentation and so on. We support all these different missions. You saw the word cloud. Here's just some numbers: Webb, Roman, Hubble, many of the solar system missions as well. How do we actually get into the data? Well, the Keck Observatory Archive has been a collaboration from the beginning between NextSci and WMKO. It was originally high res, and then one by one we kept adding the instruments without telling NASA headquarters that we were doing that, because they said you should only do high res. And we sort of ignored that. Then all the instruments, all the partners, all the time are there. And then NASA headquarters gave itself an award for coming up with the idea. I kid you not. So we have a 12-month proprietary period for NASA, 18 months for everybody else, but extensions are possible. John mentioned that the COA citations have been growing, and you can see down here that we're approaching 15 to 20% of the scientific citations of Keck come through use of the archive. NASA did support the development of real-time ingestion as part of the Data Services Initiative. So instead of overnight or 24 hours to get your data to the archive, it's now instantaneous. And the days of R-syncing to get your data are either have gone away or are going away. Are they still there, John? Okay, but it's going away. And we have some new data services. There's a new way to archive, to get access to all the contents of the archive very rapidly. Okay, so one version of the slide didn't make it in, so let me do this one instead. So prediction is hard, especially about the future. I was interested in looking up the origin of the quote. It's been attributed to either Niels Bohr or Yogi Berra. And either one, they're smart people in their own special ways. And, you know, I have no idea what's going to happen with the federal budget or the renewal of the cooperative agreement, the role of astronomy on Mauna Kea. Those are all way beyond my pay grade. And I work on the assumption of unfounded optimism, and I think this will all work out. How will it work out? I don't know. It's a mystery. So some final thoughts. Why has Mauna Kea succeeded? I think it's because of the hardworking team at Keck. Their goal is be on sky tonight with the best possible instrumentation. We have fabulous, innovative instrument builders. We're training the best students. There's strong engagement with the local community. And as we've heard over the last few days, a very actively publishing science community. So what's Keck's role in mitigating the erosion of US leadership in ground-based OIR astronomy due to the continual failure of federal funding? And I don't mean just this fiscal 26, it's been a problem going back many, many years. For at least a decade from now, Keck will be the largest US accessible large telescope on the ground. How do we take advantage of that and help the US community? I think we need to make sure we're doing fewer things better and faster, but certainly better. We want to take advantage of everything Mauna Kea and our telescopes offer us: fabulous seeing, UV coverage, field of view. These are all things that make Mauna Kea and Keck unique. I think developing impactful operational modes can be important. We saw earlier that some smaller telescopes have enormous impact in publications by just doing very massive surveys. Is that something we need to be doing in the ELT era to maximize what we get out of Keck? And then I think we want to maintain synergy with the NASA missions. And I would aver that as we give up leadership in ground-based OIR astronomy, as the ELTs come on and we wait for whatever US ELT program, it's the NASA programs that keep the US in the forefront of astronomy. and making sure that we work closely, that Keck continues to work closely with that is very important. It's also very important to keep NASA investing in Keck. So I'll end with just an acknowledgement of two people who I think were very important to me. Gary Neugebauer on the left was a pioneer in US astronomy, pioneer in developing Keck. He also led the NASA IRAS mission, and he was also somebody who believed strongly in the NASA-Keck partnership. On the right is Jerry Smith. Jerry managed the construction of the NASA IRTF. He managed the IRAS mission, and then, of course, wrangled daily with Jerry Nelson to build Keck. And they're people, who I have a real debt to, and I think epitomized this NASA-Keck partnership, which has been so important. There's certainly other people I'll acknowledge. Eric Beichman is here. He was my thesis advisor and returned me to the straight and narrow, or at least kept me on, not so straight, not so narrow, but a path, and a lot of other people. And thank you.